Welcome friends to 21st module of AI. In this module we'll be looking at the Minimax algorithm. We have looked at many other things in past. We talked about Minimax layers, we talked about the heuristic function which is called static evolution function. We've also seen that as Graham tree is expanded to the maximum possible level, static evolution function is applied at the leaf node, is backed up, and based on which you will decide the next node to choose. Additionally, we also seen the SEF being a composite structure. It contains is basically a weighted value, okay, multiple components multiplied by their respective weights. A Minimax algorithm works like that, and we are going to look at the algorithm, the very algorithm in this particular module. We are going to look at a particular version of that algorithm in a pseudocode form to understand it clearly. There are many other ways in which you can represent this algorithm. Some other authors have shown some other way but basically the algorithm is same. It's the same thing which we have studied in the previous module. You want to describe Minimax algorithm in nutshell, it's the same thing which we have done. You explore the tree as long as you can, get the static evolution function value, back the things up till the topmost node. Based on that, pick up the best move from there on every time you do it. Okay, so that is what Minimax algorithm is. Okay, it's basically a recursive algorithm. Please understand, there are three phases of any recursive algorithm that you pick up. In first thing is called winding phase. So winding phase happens before you make the recursive call. Okay, if you read any recursive algorithm, if you taken up any programming course, you probably know what I'm talking about. A recursive function is a function where a call to itself is made somewhere in between. So whatever you have done before is called winding phase, and the next phase is the recursive call to that function. The lowermost part is called unwinding phase. Now, the difference between this winding and unwinding phase is winding phase, if you call F1 and then again the next call and the third call. So winding part happens first here, then here, then here, then here in a normal conventional case. Winding part that you have written does not happen first here, happens in the last function which is invoked. That unwinding part happens there, then the next to next, then the next to next, and so on, and at the end it will come to the first function which is being called. Okay, so that is how this thing processes. So the recursive function, there are three different components: winding, call, and unwinding. So in Minimax algorithm, the exploration of tree happens in the winding phase. Call is made when you reach to the final this thing, and then unwinding phase starts. So the backing up value happens in the inverse order. We'll soon see how that happens. And basically is depth limited. Depth limited, why? Because game tree you cannot explore completely based on the time available or whatever, you just stop somewhere in the middle. Remember, we discussed about plausible move generator in the previous module. Plausible move generator is assumed here. Remember that plausible move generator is based on a given game. Okay, so that we cannot generalize. So we are not talking about, we just assume that PMG exists, will generate nodes for us. So that is assumed. Static evolution function is also assumed to be existing. We don't define any static evolution function here. And we'll see that there is something called alpha beta pruning. At the end, we'll see that there is something which is possible to be applied to this, which improves our search process. And the next module will see that thing in little more detail. In this module, we'll only mention that. One ply search is shown on in figure 20.1. It is shown. You can see that A is explored, and it is a max ply because there is only one ply search. You just play your move and get all states possible. Suppose if you have 4 possible moves, okay, B, C, D, and E, you can get either of them. So you just apply static evolution function to B, C, then D. B says it as -5 is not very good for us. C is 7, far better. D is 3 and E is -1. The best is obviously C. So you would choose to play the second. Remember, the static evolution function or heuristic is only an estimate, and I have just played my own move. I have not seen what opponent is up to. It's very hard for me to decide whether this value is the estimate is very correct or not. So this one ply search is not very good. Let us go for a second ply and see what difference does it make. Look at the 2 ply search. The same case, 2 ply search, B has 2 children. Now how I have 2 children of B? It is basically decided by this plausible move generator. I assumed it exists, so I am not worrying about that right now. C has 3 B has 2 and E has again 2. And now if you look at those values, B has 2 children, F is 5 and G is 3, minus 3. While C has 3 children, H is 7, I is minus 9 and J is 5. Same way D and E. Now if you look at this, which value out of that will be passed up? The minimum value. Why? Because his opponent is going to play. So in case number 1, now once it is backed up, the next slide shows that now B becomes minus 3. Though there is a node which can guarantee a very good that thing, but the opponent is not going to play that for us. Opponent is going to play the minus 3. Thus case number 2, a very good move called 7 is available, but the opponent will not play that. Opponent will play minus 9, almost defeat for us. My king is under attack kind of, or queen is captured. The third one is minus 3 and fourth one is minus 2. Now when I have explored only first ply, B looked promising. Explore 2 plies, B is the worst move. Think of it. So that is the issue. If you do it only once, that's a problem. That's the reason why I would like to explore the search tree as deep as possible. So we get as near accurate as heuristic value as possible. The functioning of minimax again is like what I have talked about. The player starts from some state, okay, here in this state it has B, C, D, E and further and further. When we stop, whatever those leaf node values are, static evolution function is applied and calculated. Minimum level, minimum value of the children is passed up. Maximum value of the children is passed up. Eventually it will reach to us and we'll looking at which we'll decide which out of which 4 children that we have, which one is better for us. Obviously plausible move generator and static evolution functions are assumed to exist. Before we embark on the real algorithm, there is one more word which is commonly used in literature called W and B. It is not white and black. Not only white and black, it is also the player 1 and player 2 sometimes. In most cases, if you look at those chess puzzles, you will find W and B. Okay, but and in some cases it is player 1 and player 2 as well. In some cases, player and opponent or something. Okay, so W and B are not preferred by many authors. So you may not use them, but you will find them. Anyway, so we are not using them. We are only using player 1 and player 2 here. SCF returns what? SCF returns the winning chances for player 1, not player 2. Okay, W. B chooses obviously the player B, or player 2 chooses minimum value of static evolution function. Okay, the current state, every time I have to take a move, the current state is given to the algorithm. It looks at all possible moves, next to next moves and next to next moves and so on, as long as the time permits, and once it is done, it will return back which move is better for me. I'll pick up that move. And the first call of this algorithm will take the starting state, okay, the initial state. In case of chess, all of us know what that initial state is. So that is passed to. Next time is the next one. When the opponent has already taken his move, the next move will be the next pass will be passed. So in this case, the first level, the second level, the third level, first level, the third level, the fifth level, and so on. I'll be invoking minimax algorithm. I've already told you that every recursive phase has 3 parts, and the algorithm that I'm describing also contains 3 different components: the winding part, recursive call, and unwinding part. We'll see what exactly each part is doing in this particular algorithm. The unwinding part, in most of the recursive algorithm, the unwinding part is more critical, because every function contains that. The winding, whatever is there, every function contains. Whenever you have a function call made, this is a function which calls some other function, this function calls some other function. Before that calling, every statement that is executed in this particular function will be executed before that call is. So that is all very common thing. Unwinding part, on the contrary, is very important here, because that happens in the reverse order. In many cases, the recursive process is invoked just because of that unwinding part being done in this simplified manner. Otherwise, if you write the algorithm in a different, the iterative way is going to be very tough. Unwinding start in the last function in the chain and then comes back. So that is important here. And remember what I have told you, the leaf nodes, you apply that static evolution function, okay, and then it passed up. That happens in the unwinding part of the function. Okay, when we look at the function, I'll again remind you that place. What will be the terminating criteria for? We've already seen that the time obviously is 1. Chess playing programs usually have time associated. So it says that you have 5 minutes. In 5 minutes, you'll have to find out whatever you can. So that's usually the constraint. But then we have explored enough number of plies. There was a game, there was a system called B Star, which was designed by a chess player as well as a computer scientist, and he decided that I'll explore till I get some kind of quiescence, some kind of stability in the system. So when I get stability, the moves are not changing much, the state space is not changing much, I believe that is the right time to stop, and I stop. It does not depend on that time. B Star is little different. It works this way. And we get quite accurate measurement. We believe that the measurement that we are getting now, we are very good now. Remember why we are exploring multiple plies? Because we are not sure what is unraveling later. Okay, so we would like to explore and try to figure out how good a particular move is, and go further we are more sure. But while going through it, at some point or the other, we realize that we are quite accurate, we are very good, we can come back, and for which we have written a function called over. We have not written a function over, we assumed a function call over. We have written a function, we have a function call only. Okay, the algorithm we have designed returns two things, okay, into one. There is a structure called node info, which the algorithm returns, which contain two things: the best move that I take next, and the path, okay, the heuristic value, the complete path and the depth. Okay, two things. Node info object contains this two value, and node info contains one is path, the other is value. Okay, two things: the heuristic value and the path. Unwinding accumulates the path. The algorithm does not describe both plausible move generator as well as static evolution function. We just assume it to be there existing. Now let us begin the exploration of the algorithm itself, the Minimax algorithm. We begin with the exploration. The first statement that you can encounter is Minimax. The arguments are current state, current depth, and current player. Why these three? Because we are moving in. It can be the first move, can be the third move, can be the fifth move. So what's the current state? We'll apply, we'll have to provide this current state, because unless we provide current state, we will not be in a position to apply PMG to it and generate children. That's one reason. Current depth is provided because that is going to be incremented every time. It begins with 0, but then will increment every time. So when you get back, you know where I am. Okay, so if somebody is already told us that after a sufficient depth you'll have to come back, it may be a terminating criteria. So 5 plies dip or 6 plies dip, so that depth of that ply is indicated by current depth. Current player actually is either V or the opponent. So it's basically an alternate thing. V opponent, V opponent, that way. Okay, so that also is indicator, and that indicator is important for us here because at alternate layers we are picking up either maximum or minimum values. Look at what it returns. It returns node info. Remember, node info is a structure which we are going to define later. It contains two things. One is path, which is basically a string talking about move x, then y, then z, and so on. That's the path. And the value, the heuristic value that path, that move enables us. How good or bad that thing is. Why we need that? Because just assume I have 4 different children. So for first child I calculate this value, a second child I get some value, third for I get some, and fourth also. I just got these 4 values, their path. Path is not very important, but the value is very important, because based on this value I'll decide which path to choose, which move to choose. Okay, so that's why that is very needed. Okay, the next statement is basically a terminating criteria. Again, this is a very, very important issue when you write any recursive algorithm. Before you have a recursive call, you must provide your terminating criteria, because when you make a recursive call, it goes to it invokes one more instance and will continue doing it if you have not specified a terminating criteria before. Okay, so when the terminating criteria is reached, you will have to come back. So the terminating criteria comes here. The terminating criteria is tested by calling a function called over. As I said, this over function might check many things. So we have not written this function, we have only called this function with 2 values, current state and current player. It's based on the player as well as the state. So if we have reached to the ply, in the earlier case we have found that 6 is as a value for the ply. So over might return come back when we reach the 6th ply. Okay, so when we reach there, what should I be doing? I should be returning 2 things. One, the heuristic value of this, In fact, I won't return without doing a process. I'll have to back the values up. Okay. So, for that I have that value and also the path from where I am connecting, what's the exact path and what's the heuristic value of that particular path. So, these two things are being sent back. You can see that the body of part describes, it says node info nf is a new node which is defined. Nf dot path is null. Now, why the path is null? Because you're going there, now you stop and now you're returning back. The path is accumulated in the inverse order. So, it begins with null, but when it goes up, it adds that thing. Then again it goes up, add that component. When it reaches to the calling node, will have the complete path. So, it begins with null. What is the value? The value is, and remember, static evaluation function only applies at this place, it is not applied elsewhere. This is the time where I have reached, when reached to the leaf node. I have reached to the leaf node, apply static evaluation function, okay, and then that value is written back. The static evaluation function requires two things, current state as well as player. Based on this two, it comes back with static evaluation function value. Okay. I could also have specified current only, okay, current state only, but providing player will give you a better idea about how good or bad that function is. Okay. The over function thus returns the structure. Okay. So, node info structure, which is very important for us. If it is not a leaf node, the function proceed further. It is not a leaf node, what should it be doing? It should generate the children. Okay. So, that is exactly happening next, is calling PMG, and PMG generates children for that particular node. And if the children list is empty, there is no children, okay, what could be the case? The case where you already reached to a dead end, okay, we can't proceed further. It's kind of a draw. In chess, it is possible to have a situation where you cannot proceed further. There is no way to proceed further. So, in there you don't have a children. The other case where you already won or lost. So, but it's basically a leaf node. Okay, though we say that we'll go out 5 plies diff, at the third ply itself, you have reached to a dead end. So, that's the case. It's exactly similar to a leaf node, and it's treated exactly in the same fashion, which is the next state in the game itself. If this is also not the case, we have multiple children, what will we do? We'll find out the best child out of it. How we do it? We will initialize the best with whatever minimum value. Then we apply static evaluation function to each children, each one of them, and then find out the best out of it. The best applying that thing will get us best static evaluation function value, and that will pass up by and that's quite interesting. We are multiplying it with -1 and pass it up. Why we are doing it? Remember, we have to find out maximum value in case of a maximizing play, minimizing at the minimizing layer. If you do not want to do it, just negate it. If you negate it, you always have to apply one function maximizing and you will get the same answer. For example, if I want to find out minimum between 1, 3 and 5, then I -1, -3 and -5, when I apply maximum, I get the same answer, irrespective of the sign. I am not bothered about the sign right now, but because I am not worried about 5 or -5, I am worried about the child which returns that. So, I will pick up that child, the third one, if I am doing it. So, that is the issue here. So, that is exactly what is happening here, and it is in PPTs, it is bold faced. So, you can see that the call is made to minimax for every children. The second step, though it is non-leaf, we will consider it to be leaf and proceed further. Remember, why? Because we have no children. The third step obviously goes ahead and calls the minimax for its children, incrementing depth by 1 and converting player into the other player, and also negating the values. If you have seen the algorithm cleverly, you would see that the value that we return is also written in negative form. Okay, so heuristic value also is negated. So, you do not require to apply minimum, it is always maximum. The fourth step is collection of nodes and whatever we have discussed, and we have also studied how we decide the best value and why that best value is good. Okay, the only point left out so far in this particular discussion is that what will be the first call. Okay, there are 3 arguments passed to the algorithm, the current player, the depth value, and the heuristic player's identity. So, the call here is current state 0 current player. Current state 0 current player means current state is the state on which the minimax is applied. 0 is the depth, we begin with 0. And the current player, player or the other one. In the beginning, we will start with start state 0, 0. Why? Because start state is the first state, 0 is the depth, and 0 is the player who is playing. So in the beginning it will be this, later on it will be the other one. And if the opponent starts playing, in chess it is possible that we may not start, the opponent may start. The first case it is minimax start state 0 and 1. Okay, so with this almost have completed minimax algorithm. The remaining part talks about a very simple improvement that we can make. Look at the first figure talking about alpha cutoff. We'll be discussing about this in more depth in the next module. But you can see that I'm exploring J. Should I explore J? In the beginning you may prefer that yes, it is 5, it is good, so we should. It is not. Why? Because the opponent is going to play, and there is an alternative called I available, which opponent can play, which leads to almost defeat for us -9. So even if I explore that node will give me 10, it's of no use because opponent is not going to play that. It is not going to allow us to win. Okay, so there's no point exploring it. And the other reason is that I have -3 already. See, I'm a player. I have B and C, two choices. And if I play B, I'm guaranteed to get -3. Okay, I'm guaranteed to get -3 or more. If the opponent makes a mistake, I may even get 5. So I have that option. I'm not going to play C. That's the other thing. I'm not going to play C. What's the point? Because it's quite worse. -9 is worse than my -3. So I'm not going to play C. So there is no point exploring J. Now when you provide this cutoff at minimizing level, it is called alpha cutoff. Now you can see something quite similar in the next slide. I'm exploring one more child of I after I explored P. Now I've already got 5, which is very good. Now why should I be not exploring the next one? Please understand, opponent has two options. H is already given at -9. So given an option, opponent will obviously pay. So if opponent plays H, there are two options, -9, 9 and 10. He is guaranteed to get -9. If he plays I can play P, which guarantees me 5, which is very good. So opponent will not choose that, irrespective of what is the value of the other one. Other one may be 10, but that is better, but is always 5 or more. If it is less, I'm not going to play that move. I only play P. Okay, so the point is there is no point exploring the next branch. That makes it an important cutoff here, and this happens at maximizing layer. A cutoff happening at maximizing layer is called beta cutoff. So these alpha and beta cutoffs are also applied to minimax in most cases, which improves the algorithm further. With that, we'll complete this discussion on minimax algorithm. What we have seen in this particular module, we have so far looked at the minimax algorithm itself with the structure, node info, the recursive version of the algorithm, 3 different components of a recursive algorithm, and how minimax actually does all these jobs, how minimax algorithm continuously recursively calls itself till it reaches the leaf node, and applying static evaluation function there, and then backs the value up in the unwinding part and chooses the best move. We have also looked at the alpha and beta cutoffs at the end of this module. With that, we will come to a close. Thank you.